Hello everyone. The clock has just hit 2. I see people are still slowly joining in, but yeah, let's just start on time. Welcome to this webinar. This is the What's New webinar about timber for version 22.1 of SCIA Engineer. It's a minor SCIA Engineer release, but for timber, it's one of the biggest releases recent times, and I have the honor of presenting you these new features today. I myself am Jael Verkammer. I'm a product manager at SCIA, responsible for mostly the material design inside of SCIA Engineer. So yes, welcome everybody, and let's get into it. As usual, before we start the webinar, the little explanation about GoToWebinar, the tool we are using for this webinar. During the presentation, you will all be muted, but this doesn't mean that you cannot ask your questions. You can ask your questions in the question box of GoToWebinar. I have 2 colleagues here that will help me out and reply to your questions in written words during the presentation. Or if not possible, I will reply to them also at the end of the presentation and give you some more details, maybe show extra stuff. But we will keep this for the end of the webinar because this part of the webinar is being recorded and it will be put online on our SCIA YouTube channel afterwards so that you can rewatch it if you missed something, or share it with your colleagues if they are also interested. Tiny sip of water. And let's go look at the agenda. The topic of today will be an extension of our CLT Autotropy. So in version 22, we introduced some orthotropy parameters where you could define your CLT panel geometry and it would automatically calculate the stiffness parameters. And we have improved this orthotropy function. Next up, we have added an ULS, an ultimate limit state design of the cross-laminated timber panels that I will show you later. And finally, we have done some SLS improvements for the 1D timber check. And also I have one tiny extra side topic at the end that got added last minute. But first, let's go look at the extension for the CLT Autotropy. In the old version, well, not really old, in version 22, we added this orthotropy for cross-laminated timber, but there were still a few parameters that you had to manually introduce, being the torsion reduction coefficients, shear stiffness coefficients, and shear correction coefficient. And of course, you need to introduce the number of layers for your panel and thicknesses. These are logical. But these parameters, it can be quite more complicated to find the correct value for them. In this brand new version, 22.1, we have offered for all of these options a way to calculate internally by SCIA Engineer the value that these coefficients should have. For the shear correction coefficient method, it is calculated in the background by some finite element analysis. And for the other 2, we are following a method from the norm from Austria, because the general Eurocode doesn't really give an indication on how to calculate these coefficients, but luckily our friends from Austria offer a possibility, a way to calculate it. In my next slide, you can see a little bit the formulas used for calculating these coefficients. And yeah, you can now automatically let SCIA Engineer calculate those coefficients for you according to the norm. All of this information on how the calculations are done, you can find them as usual on our help.scia.net website. I will show you this also later inside the program, but first let's have a look at the cross-laminated timber design. First, what do you need to be able to run the cross-laminated timber design in SCIA Engineer? You need to have the timber module activated in your license. So either you have a concept edition or a professional edition, or you have the module by itself. As long as you're able to design timber, starting with version 22.1, you will be able to run the CLT design. If you tried it before this Monday and it wasn't working, it's because it's normal. It was added on Monday to the license. So yeah, starting the beginning of this week, you are able to run the CLT design. Next up, you need to have a CLT material defined in your project, else it will not be possible to run the check. By default, since version 22, there is a CLT material in your project. But if you are importing an old project, be sure to make an extra CLT material, and then you will be able to do the CLT design. And of course, before you're able to run the design of an element, you need to have a 2D element with the CLT Autotropy assigned to it. If you just have a timber 2D element, it's not sufficient because it could just be a plain timber plate. How does it work? Well, we've already seen the way to define the autotropy, and this autotropy calculates a mean stiffness of your cross-laminated timber panel, and this mean stiffness is used in the calculation, and this calculation will return us the internal forces. Then these internal forces are given to the check, and the check will recalculate the stress distribution in the layers of the panel based on the internal forces and, of course, the properties of your CLT panel. And then finally, those stresses can be checked according to the code. So what's possible with the CLT design? The CLT plates will be designed according to what will be the next generation Eurocodes for timber. They include all of the typical checks that you can see on the screen. I will not go over them, but they are the standard checks. And they all come with the well-known detailed output with formulas, references to where the formulas come from in the code, and also possibility to display the stress diagrams so you can see the stress distribution over the layers of your panel inside the report. And all of this indeed for forming a transparent check so that you can easily see every value, where it comes from and why in your check. Also, this check is compatible with all of the other possibilities that we offer for 2D checks. For example, averaging strips to average out the stresses over some support area, for example, or the advanced option for display of 2D results with ISO bands, with ISO lines, colors. Everything is compatible and can be used also for the CLT ULS design. And now I will be brave and show you both of these topics live in our 22.1 version. Let's start by simply, if I find my mouse over there, yes, I do, by simply making a new project so I can show you how it works from scratch. Of course, I need timber to be activated, and you will see immediately that from this version, there always will be by default one cross-laminated timber style material. You see it here, type of timber, cross-laminated. So if you have to create your own, just make sure you put this type of timber on cross-laminated. Why? Because it adds some extra values like the rolling shear resistance here that are needed for cross-laminated timber panels and not for the typical timber. laminated timber material. Yeah, the rest is fine. And let's first go have a look at the autotropy. So here we have our autotropy, and we can change the type of autotropy to cross-laminated timber. If this one is not available, it's because you don't have a cross-laminated timber material in your project. This one CLT, so I don't get confused later. You can choose your material, the number of layers. As I showed you before, now instead of having to manually input the coefficients, there is an option to let them be calculated automatically. And also here for the shear correction, it can be either manually inputted or calculated through a finite element analysis. If I change, for example, the number of layers, you will see that in the background, there is a quick calculation that's run, and the stiffness coefficients get adapted accordingly. The OK button has disappeared a little bit. It's because I'm working with my TV screen and it doesn't like laptop functions, but this is fine. Now let's some plate. CLT material, that's good. It's not an isotropic plate, but it's an orthotropic plate, and I will choose my CLT Autotropy. You'll always have to look for the OK button apparently. And let's input 0.66, for example. Okay. Zooming on my little structure. There we go. And adding in some loads. Something happening. Surface load. And a 2D number. There we go. Let's say 3 kilonewton. And of course, some supports. Bear with me, this is the only part that's going to be slow. Oh, this is a line force, not a line support. My bad. Line support, please. But then you get to see the whole process from scratch, what you need to do if you wanted to try it out yourself. Quickly run a calculation because, of course, we need some results. And that's it. If we now go to the timber menu, we can find the cross-laminated timber ULS check. And say we run it for a combination, I refresh, and the check is executed. We can see that's mostly my plate satisfies, and if I open the report preview, I can see that my highest unity check is 0.62. I can see for which combination, I can see the positions, etc., as you are used to from SCIA Engineer. Also possible is to define the averaging strips. Currently, I don't know how averaging. So we can nicely see the influence on the results. Let's go back to my check, and here I can say that I want to account for the averaging of the peak. Now you don't really see a big difference like this, but as I told you, everything is compatible with the settings we have. So for example, if you want to see more details on how the unity check is varying over your plate, instead of having the 3 colors, we can go for the isobands view. Okay, refresh. And now you can nicely see how the unity check evolves over the plate, and we can see that the averaging strips, for example, can be taken into account. All right, let me quickly close off this one. don't need it anymore, and open an actual project. Hope that you guys are as excited as I am with these new developments. It's really cool to see check for some brand new material out here. Yeah, so here I got us some real projects. We can see that's also partially failing the check. And what I wanted to show you on this side is the detail output with the formulas, and also this new option, print pictures, that's activated, where I can get into the report now. And you get the entire detailed output of everything. The location, our maximum unity check, the combination key, safety factors, material factors, forces, the CLT, stiffness values, and then the checks are also displayed. The tension check with the pictures, the compression check with the pictures, bending with the stress distribution, nicely showing the layers contributing of our CLT panels, the bend the other direction. We have the transfer shear, where you can see the shear contribution and the rolling shear of the in-between layers. And yeah, all of the detailed formulas are there, and the references to, I see that I missed out on having the tables and formulas as well. I was already wondering why I couldn't see them. Yeah, so now we have the little tables there as well. And yeah, you can see the entire check for every component that was mentioned in my slide, including flexural buckling at the end. And here we see that the buckling length of my plate is set to 4 meters. Unfortunately, our software is not smart enough yet to detect of your panel what its buckling length will be. Mainly if you are going to draw some weird shapes, it will become very complicated. So for the buckling length, you can go to the timber settings, the buckling defaults. There is now an extra menu for 2D members, and there you can define the default buckling of your panels. But of course, not all of your panels have to have, or not all of your walls have to have the same length. So there's also an option to have some local member data on our panel. And there we can actually individualize the global settings per individual panel. For example, we can change the service class, the system strength factor, if you want to have a different one applied. You can change the buckling default length from following the setup to inputting it manually, and then yourself giving a more appropriate length for your member. Okay. And then this one gets taken into account, of course, in the calculation. Maybe you can take my word for it, but I will have you have 2 seconds for patience, and I will show it to you. So our buckling length has now changed to 2 meters. So that's it for the CLT design, and I will take you back to my presentation for our final, well, not final topic, next to final topic, the timber SLS improvements. For those of you that work both with the steel material and the timber material inside of SCIA, you know that the SLS design from timber has quite some shortcomings compared to the steel SLS design. But all of this is now remediated. And yeah, we have improved quite some stuff. The first one is that there are more output options. You can show the KDEF, you can show some intermediate results of the deflections, like the instantaneous deflection. You can display the deflection limits. not only in the reports or in the result tables, but also on the screen. So you can show the final deflections of your structure on the screen instead of like previously only the unity check. We also simplified the limit settings for the deflections, where previously they were still going off the type of member that you have, and now they have been aligned with how it works for steel, where you have one global default, and then anything changing from that default can be set inside the buckling settings. Also for cantilevers, automatically they are handled if your beam is in a cantilever, doesn't have a support on one side, the deflection limits get divided by 2 automatically, just like for steel. Also, we have enabled now to run the SLS calculation on timber for nonlinear combinations. Previously, this was not allowed. Mainly the issue is that in nonlinear combinations, it's hard to know which part of contribution is coming from which load case, because the results are not linearly decomposable. But we still offer a solution for it, where we will look at the linear calculation, the ratio between the load cases there, and we will use the same ratio on your nonlinear results to define an SLS calculation there. So yeah, it's a compromise to be able to get results for SLS in nonlinear combinations. And finally, we have added also the camber design, both input and design. So if you want to input some predefined values, that can be done, or you can let the software design for you the camber necessary to make your structure satisfy the SLS check. Let's go ahead back to SCIA Engineer and show this to you. I will have to quickly switch projects again. Let's take a timber hall that seems good for showing SLS design. I have already pre-calculated here. We are in the timber menu and we find the timber SLS check. It works as you expected previously, not much changes. On this side, I can run my SLS check for my SLS combinations and I get my unity check. However, if you open the report preview, you will already notice some difference, that there is quite some more information shared with you. You get the results for the instantaneous deflection, the net final deflection, which is the deflection taking into account camber, and the final deflection, which is the instantaneous and long-term deflection, but without the camber included. Tiny drink break. Okay. We also see the limits for each of the directions and then the unity checks for each of those. Finally, we can see if there is camber, we can see the deflection of the camber at the position of this section that's being checked. We can see the biggest camber value over the span, and we can see the value of KDEF that was used in the calculation of the deflections. And of course, our global unity check is displayed at the end. All of these values that we've seen in the report can now also be shown on screen. So if I am going to maybe in the Z direction makes more sense, I can display the net final deflections, and I can then see my values in millimeter on my structure instead of only being able to display the the unity check. And you can also display the limits, the camber that's been defined on your structure, etc., etc. This can all be visual. In the settings, we can go to serviceability limit state. Here you can define your global limits for the 3 values, for the instant deflections, for the net final deflections, and for the final deflections, for both in plane and out of plane deflections. And then if you want to design camber, you can either activate the design for camber and then choose your camber shape, set up your limits and your roundup values, or you can choose to input your camber relative to the length of the member or in absolute values. It works absolutely the same as for the steel code check, so that should be familiar to most of you. And then finally, if you want to override a limit, you can select a member, go to the buckling groups. There we go. We go for the deflections. You can change the deflection limits, not from setup, but I want to define them either for all of the spans of the beam at the same time, or even a different deflection limit per span of my beam. And I can input them in the table if I change them. And for camber, you can also choose to design camber only for specific elements by setting them in the member settings. All right, time flies, so it's time to get back to my presentation and move on to the final point of today, which is an added option that's still being developed further. It is a connection to our sister software Frilo. Frilo has Frilo HO13+, which allows the calculation of timber truss connections. And it is now possible if you have in SCIA a project that's calculated with linear combinations, you will find the Frilo timber connection option, and it will allow you to export your node to HO13 and design it there according to the German, Austrian, and British NA. Our goal is to extend the possibilities in Frilo and NAs to the future, and also, of course, to link to more of their options. So definitely this will be extended to the future wise. And yeah, for now, make sure if you are trying it out that you have hinged diagonals and that it is a 2D node you're calculating, because Frilo only is offering a 2D solution. So you need a 2D node, linear combinations, and then you can transfer this node to Frilo and design it. And that was my last topic. So we got to the questions. I will go have a look in the chat. I have seen some actions. But if you still have questions, feel free to ask even more. Are there fire checks available for the CLT module? At the moment, it's not implemented yet, but what you could do is actually calculate how much millimeters of your layer you will lose to the fire, and actually reduce this in your CLT definition, and then rerun the check with your fire situation. And this way you could simulate a fire check. I see another one about fire check. Can a deflection limit be set for different load cases? If you mean that the deflection limit should be different per load case, then unfortunately, no. So as I showed you, it's possible to define a limit for the instantaneous deflections, for the final deflections, and for the net final deflections, which is the final deflections including the camber design. Okay, For the rest, I don't see anything that wasn't handled by my colleagues. So, is there a timber module in the student version? Yes, the timber module is inside the student version. So if the students are running version 22.1, they can, of course, design CLT as well. All right. If there are more questions that weren't answered or you're curious, want to learn more, you can always send your questions over to our support at SCIA.net. They will transfer them to me and I can give you more detailed responses. But for now, I think we can close off the webinar. Yeah, I hope you enjoyed it. I hope you will enjoy the new features, play with them, and I hope to see you again in one of our next webinars. Thank you all for attending.